Hello, everyone. Dr. White back again with the first in a series of screencasts on section 5.1 of our textbook. This is on estimators and their variability. Beginning with this section, we transition from the considerations just of probability, which was the subject matters of chapter 3 and chapter 4, into applying probability to inferential statistics. So we're going to start really learning how to use data to make inferences about the underlying features of the population or the process that produced the data in the first place. And probability will be a key tool in that enterprise. So, beginning a new chapter, we take a look at our studio to see if we've kind of cleared things up and set ourselves up well. If there are any old files that we don't need anymore, like there's the old DA, then I'll just close it out. I check to see that my global environment is empty. And I'm looking in my home folder. And why don't we just go ahead and say session restart R. So now we're all starting off fresh in the same place. If there are any packages that are required in our work for this chapter, we'll need to remember to attach them to this R session. All right, let's go grab section 5.1 slides. //com Dr. White stuff, Math 111, slides, section 5.1 estimates variability slides. Press the blue text, view in web browser. Up it comes. Variability in estimates. Oh, well, we're going to need some packages today. Library TigerStats. We'll need the TigerStats package. I copy, I head to our studio, I paste it in, and it attaches. Note that at the very end, there is an invitation to visit the website. And if you were to follow that URL, I'm just pasting it into a new tab, you do come to that website for the package that I've told you about a couple of times. But back to the slides. So I need to give you some definitions of some new concepts. Parameters and statistics. First of all, parameter. A parameter is a number associated with the population. It does not depend on chance, but usually it's unknown. A statistic is a number that we compute from the sample data that we've drawn from a population. It can be known because we have the data, so we can use the data to compute it. But it depends on the sample, and so it depends on chance, unlike a parameter, which does not depend on chance. What are some examples? Well, often a statistic comes in the form of what we call an estimate for a parameter. For example, one number that's associated with a population is maybe the mean of the population. Like if everybody in the population has a number and you average up all those numbers, that's the mean of the population. That parameter is called mu for short, the Greek letter for m. Now, if you take a sample from the population, then you might compute the mean of that sample. That sample mean is called x with a bar on top of it. And it's a statistic because it's a number that you compute from your sample. Now that population out there It always has that same mean. But different samples would have different data in them, and so they would have different X bars. The estimator, the X bar that's used to try to estimate the mu, depends on chance because it depends on the sample, which depends on chance. Another example, another parameter is the standard deviation of the population. So if you just arranged all the items in the population in a list and computed the standard deviation as we learned to do so in previous chapters, that number would be called sigma for short. It's some fixed number for the population, but it's one that we're not likely to know, because after all, we don't have all the numbers in the population. We can take a sample from the population and we compute the standard deviation of the sample. That's called S for short. S is a statistic, and that sample standard deviation is used to estimate what the population standard deviation might be. It goes on. The population of numbers maybe has a median. You arrange all the numbers in the population from low to high and pick the middle number. That's the population median. You take a sample from the population, you can compute the median of the sample, and you might use the sample median to estimate the population median. Population median is a parameter. The sample median is a statistic because it's computed off the parameter, and it's used to estimate that population median. In the same way, the third quartile of the population could be estimated by the third quartile of some random sample from the population. Statistic, parameter. Fixed, 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 fixed. Depends on sample, so depends on chance. 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 Each of these is used to estimate its corresponding parameter. That's our hope. These statistics that we call point estimates, we're hoping that they'll be decent estimates of the parameters that they're set up to estimate. There are 5 basic parameters and correspondingly 5 statistics, 5 point estimates for those parameters. If you've got one population in mind, you might be interested in the mean of that population. The corresponding point estimate is the sample mean of that sample from the population. If you're thinking about one population, you might be interested in the proportion of that population that has some characteristic. And that could be estimated by taking a sample and looking at the proportion of the sample that has that characteristic. The parameter is called P. The point estimate is called P with a little hat on top. Hat in statistics means it's some kind of estimate based on a sample. Sometimes you're interested in 2 populations and may be interested in comparing their means, the mean of one population minus the mean of the other. Maybe mu1 is the mean of the first population and mu2 is the mean of the second, and you're interested in knowing what mu1 minus mu2 might be. You could take a random sample from the first population, another random sample from the second population, and compute the sample mean of the first sample and the sample mean of the second sample, x1 bar and x2 bar, and subtract those. That single number formed by the subtraction is a statistic, and it is a point estimate of this parameter. Similarly, if you're thinking about 2 populations, you might actually want to compare 2 proportions associated with them. P1, proportion for the first population, P2, the proportion of the second population that has that characteristic. What you might do is take a sample from each population and compute the sample proportion from the first population, the sample proportion in that first sample, the proportion in that sample that has that characteristic you're interested in, minus the proportion in the second sample that has the characteristic you're interested in and subtract. That's one single number, and that point estimate, that statistic, is used to estimate this parameter. There's another parameter, the mean of differences, that can be estimated by a sample mean of differences. Why don't we just hold off a discussion of that until we meet that situation in a later chapter? Let's practice a little bit to see if we can identify in a given situation which of these big five parameters might be the parameter that we're interested in, and what statistic would therefore be used to estimate the parameter. Consider this scenario. In a survey, 100 college students are asked how many hours per week they spend on the internet. So every student is asked this question, and you can imagine the students' answers: 5 hours, 7 hours, 2 hours, 12 hours, 13.3 hours, and so on. What is the likely parameter of interest? Which of these parameters is the statistician probably interested in knowing when the statistician asks this question of each person in the sample? Well, I'm thinking to myself that the question is asking for a number: 2 hours, 5 hours, 12 hours, 13.3 hours. And we're thinking about one population here, the population of all college students. So I'm figuring that on this list, we're thinking about this first parameter, the mean of one population. The way you might define it is that the parameter you're interested in is mu, and it's equal to the mean number of internet hours per week for all college students. So it's a number that we don't know because we don't have data for all students in the population. It is a number that we might estimate through a sample. Try again. In a survey, 100 college students are asked whether or not they cited information from Wikipedia in the papers they wrote for their classes. What's the likely parameter of interest? Well, here, when you ask that question, a person could say yes. Another person could say no. Yes, I have cited information from Wikipedia in my papers. No, I've never done that. Well, here, when the question is a yes-no type of question, a question where there's two possible responses, you might be interested in tabulating how many said one of the responses, like the people who said yes. Maybe you're interested in the proportion of people who would say, yes, I have cited Wikipedia in my papers. Well, when you're asking a yes-no type of question, the parameter of interest is probably P, the proportion of some single population that has a certain characteristic. In this case, the proportion of people in the population who have the characteristic of having cited Wikipedia in a paper. And so you define it this way. Let P be the proportion of all college students who cite information from Wikipedia as part of their papers. Try again. In a survey, 100 college students are asked, what percentage of the time you spend on the internet is part of your coursework? Again, what's the likely parameter of interest? So I'm thinking to myself, well, somebody could say, I spend 25% of my time on the internet doing my college coursework. Another person says, well, I spend 70% of my internet time doing college coursework, and so on and so on. People are being asked for numbers. Those numbers are percentages, but they're numbers between 0 and 100. Because there are numbers, and because there's one population here, all college students, I'd say we're interested in the mean of one population. And we can define it as this. let's let mu be the mean of the percentages of time spent on the internet that is part of coursework for all college students. You can average up all those numbers that they would give: 10%, 20%, 15%, 2%, 78%, and so on. Average them all up for the whole population. That would be your mu. So this is a little, you have to be a little careful here. When people mention percentages, you often think about yes/no questions, but this is actually not a situation we're interested in a population proportion. We are interested in a population mean. We did not ask a yes/no question. We asked a question about a number. What is the number percent time you spend on your coursework? Now, there's 5 important parameters of interest for the rest of this course, but we need to start somewhere. So in this chapter, we're going to work mostly with one population proportion P. There'll be a tiny bit of work with some of the other parameters in the DA, where you identify what parameter is of interest from a scenario. But for learning how inferential statistics works, kind of our first start, we'll focus on just the one population proportion P scenarios. Later chapters will address the other 4 members of the Big Five. That's all for now. In our next screencast, we'll dig into learning more about inferential statistics when you're interested in knowing about the proportion for one population.